Hello everyone. So in today's class, let us start with the frames. So we have already dealt with beams. That is analyzing the beam using slope deflection method, finding the shear force and bending moment. And now let us let us have a detailed study on frames. That is so as we all know, frames are basically members which have both vertical members which are connected together with a horizontal member. So that's how it's called as a frame. So this is called as a framed structure. Okay. So every building is a framed structure, after which to cover up this columns, you can see here, these are columns, and these are beam, horizontal member beam and column. If they're connected like this, then it becomes a frame. Okay, so now, so first thing is analysis of the frame without sway. Again, there are two types in this. Whenever we're studying about frames, one type of frame is the frame. If you try to apply a force here, it will bend. That is called as a sway frame. You can see here, this is the initial position of the frame. When the load is applied here, you can see load W is applied here. It will sway to the right side. Okay. So sway means movement. Horizontal movement is called as a sway. Okay. So this is a sway frame. You can see here how much it is swaying. Means how much is the horizontal movement? It is nothing but delta. This is the initial position. You can see this dotted line is the final position. So initially it is A, B, C, D. When you apply load, B becomes B dash, C becomes actually, I'm sorry, this is not D dash, it is C dash. Okay. So B becomes B dash, C becomes C. That means it is changing its position. So that means it is swaying, it is bending, it is having a lateral movement. Okay, so this is frame with sway. Okay, frame with movement, lateral movement. Okay, now if you check out, just by seeing the frame, you can make out. So actually A, D and all are connected, and at B, if you apply load, okay, obviously it moves to the right side. But at C, there is a roller support. Now, because there is a roller support here, if you apply load here, what it does is it tries to push it back. This support tries to push it back to its original position. And that's why this is called as a unyielding, that is sway is prevented. That is lateral movement is prevented, stopped. Okay. So next, if you see here, even this is the same case. So A, B, C, D is fixed like this is the frame. And at E, there is extra another member CE, which is again at E, there is a uh, fixed support. Now, because there is a fixed support here, if you apply load, what the support will do is it will try to push it back. It will try to push it back to its original position. And that's why the sway, that is the lateral movement, is prevented. Okay. So for your study, we have two types. That is a frame with sway and a frame without sway. That means both the type of frames are to be analyzed using slope deflection method. Okay, now you can see here, this is a frame, simple frame A, B, C, D, and exactly at the center there is load applied. Now, if you cut the section, means exactly at W, if I try to cut the section, left side also it is same, right side also it is same. That means it is symmetrical. When I cut the section exactly at the center, if you see to the left side or if you flip the left over the right, it will still be the same. So LHS is equal to RHS. That means it is symmetric. Now because of its symmetry, it will not sway. Okay, if you apply load, now see here, all the previous forces what we had seen was load application was at this side. Now because it was this side, obviously it would bend. Now the load application is vertical. If the load application is like this, that means exactly at the on the beam. Okay, in this beam, if you apply a load which is exactly at the center, now because of its symmetry, it will not sway. That means it will not move or bend. Okay. Similarly, in this case, now it's A, B, C, D. Again, same thing. Now, in this case, there are two loads. Now, because there are two loads, see here, exactly at the center of this, if I cut the section, if I cut this frame at the center and I flip this over, Okay, if I cut this section at the center, now you can see LHS, one load, RHS, one load, W. So LHS is equal to RHS. So again, that is a symmetry. Now, because it's a symmetry, this will not sway. Okay, just by seeing the problem or just by seeing the structure of the frame only, you can make out. Okay, next, this portion. Okay, and now again in this portion, A, B, C, D. Okay, to the right you apply load here, W. Okay, that is in column section now. You apply load W in the column section to the right side. Then CD again in the column, if you apply another load W to the left side. So right side load is equal. Again, if you cut the sections here, cut the section like this. Both are symmetrical. Both are symmetrical. And again, in this, the frame will not sway. The frame will not move. Okay. So all are these standard cases of sway type of frames. Okay. So let us take a simple example. Okay, now see here, analyze the frame by slope deflection method and bending moment diagram. Now again in this problem, what they've asked you to find out is, there is a UDL here. Okay, again by seeing the frame, you can make out whether it is sway frame or a non-sway frame. In the question, they will never mention whether it is a sway or non-sway. You have to see the frame and analyze whether it is sway or non-sway. Okay, now just seeing the problem. Now you can see here, cut the section like this, exactly the center. So left side and right side, both look similar. Both are same when you cut the section. There is a UDL here also, there is a UDL here also, right? Okay, so now it is a sway frame. Okay, because for non-sway frame, you have a different procedure. Okay, so now it is a simple frame where there is a non-sway. That means there is no movement happening. Okay, so it is symmetrical. So if it's symmetrical, it's a non-sway frame. Okay, so as usual, let's again start solving. Same, everything is similar like before. First is finding the fixed end moments, slope deflection. Okay, arriving at the slope deflection equations, then joint equilibrium equations, finally the final moments. Everything is same. And then drawing the bending moment diagram is different. I'll tell you how to do that. Okay, so let us start with this. So it is a non-sway frame. So non-sway frame, you have to always write this statement. This is very, very important. Due to the symmetry, no sway in the frame. There is no sway at all in the frame. Okay, so again, just check out. This is 4 meter, this is 6 meter, and again, this is 4 meter. All right, first is the fixed end moments. Okay, fixed end moments, that is AB, BC, CD. Okay, now, as usual, it's AB is one member, right? So, MFAB is equal to MFBA. Now, there is no load only in this member. So no load, obviously no movements taking place here. So those movements will be equated to 0. Okay. So MFAB is equal to MFBA. Similarly, in CD, there is again no load. MFCD is equal to MFDC. Okay. There is no load only here, like this, horizontal load, nowhere. So it is a there is no load taking, no load, so no fixed end moments. So MFAB is equal to MFBA is equal to MFCD is equal to MFDC. Okay, is equal to 0. Okay, there are no loads. Next, MFBC. Okay, so MFBC is equal to, okay, so it's a UDL. So we know MFBC is equal to minus, first from B to C, minus WL square by 12. Okay, so minus WL square by 12. So substitute the values, it's minus 120. Similarly, CB is plus WL square by 12. Same thing what you have done before. So it's like we found out the fixed end moments. Okay, next is slope deflection equation. Okay, in slope deflection equation, as usual again, MFAB is equal to, okay. Now see here, again in this problem, you'll know how many unknowns are there. See, theta A is fixed. So rotation is 0. Theta D is also fixed. So rotation is 0. That is theta A is 0, theta D is 0. What exists here is B and C. So theta B also exists, theta C also exists, because they are intermediate joints. Okay, it's as good as opening the frame like this. If you open the frame, okay, this A, it goes on top, C, D goes on top like this. So B and C will act like a simply support. Okay, that's why there is a rotation here. All right, here we cannot show simply support or roller support here. So this is treated like a simply support, and there exists the rotations. Okay. All right. So slope deflection equation, MAB is equal to MFAB plus 2EI by L, then 2 times theta, because A is the first member, 2 times theta A, 2 times theta A plus theta B minus 3 delta by L. Okay, so after writing this formula, so MFAB we have already found out it is 0 because there is no load here. Then it is 2EI by 4. So it is length. So again, theta A is a fixed support. So fixed support becomes 0. And again, there is no settlement here. No settlement here. So that's why it is 3 delta by L. So 3 delta by L, no support. So again, this term also becomes 0. So we are left with 2EI by L into theta B. So theta B is the only value here. So we have got MAB equation. So this is the first equation. Likewise, find the second equation, that is MBA. So MBA, write the complete formula. So MFBA, again, that tends to be 0 because there is a no load, and 2EI by L. And again, write it in a sequence only. Theta A first, then the first term here is theta B. So multiply it with 2. So 2 times theta B minus 3 delta by L. Again, there is no settlement. So both this term becomes 0, and theta is a fixed support, even that becomes 0. So finally we're left with only theta B value here. So it is only EI theta B. So this would be equation number 2. Okay. Then MBC. Find the next equation, that is MBC is MFBC plus 2EI by L. Again, B is the first term here. So 2 times theta B plus theta C minus 3 delta by L. Okay, now again you have to be careful here, because in span BC, it is a value wherein there is I value becomes 2I. Okay, I becomes 2I. So that's why you have to substitute here. So 2EI into 2 times I divided by length. And theta B and theta C, both are simply support here. So both exist. So only this term tends to 0. So finally we're left with this equation. So MBC, so this would be the third equation. Likewise, MCB. MCB is equal to MFCB plus 2EI by L. Again, theta B, write it in the sequence, theta B plus, the first term here is C. So it is 2 times theta C minus 3 delta by L. So substitute all the values here, and you'll get MFCB. So this would be the fourth equation. And then MCD is equal to MFCD plus 2EI by L, 2 times theta C plus theta D minus 3 delta by L. Now you can see here theta D, again it is a fixed support. So fixed support and settlement both tends to 0. So we are left with only EI theta C. Then MDC is equal to MFDC plus 2EI by L, 2 times. So first term is theta D. So theta C first plus 2 times theta D minus 3 delta by L. So it is MDC is equal to 0.5 EI theta C. Okay, once you get all these 6 equations, then you have to find out the equilibrium equations. That is the third part of the question. So third step is joint equilibrium equations. So again, joint equilibrium equation would be just the same what you have done before. MBA and MBC is equal to 0. The second joint equilibrium equation is MCB plus MCD is equal to 0. Okay. So write all the substitute all the equation of MBA and MBC, and again write it in the sequence only. Whenever using this, be careful with the signs. So it is theta B first, theta C, and keep it in the equation form only, equal to a constant. Then finally MCB plus CD is equal to 0. Substitute all and keep it again in the form of theta B plus theta C followed by a constant. Okay, so these are the two joint equilibrium equations. Again, use this joint equilibrium equations and substitute in the uh, calci. So solve this using the calci, because things becomes easy. I've already told you. Again, use the equation form. There are only two unknowns here. So again, in the calci, press mode 3 times. So you'll get equation. So again, press 1 in that. Then you'll get two unknowns. So choose two unknowns and start substituting these values. So first theta b value, theta c, and 120. Then again, same thing, theta b value here in the second form of the equation, theta c minus 120. So when you solve it in the calci, you'll get ei theta b value and ei theta c value. So it is same. Okay, ei theta b is plus, ei theta c is minus. Again, why you have this plus and minus is because just by seeing the equation, you can get to know. The first term is 2.34 theta b. Second term is 0.67. And the constant is plus. The same thing is in this portion. See here it was ei theta c. Here it is now 0.67 ei theta b. Okay, ei theta b value becomes 2.34 ei theta c. That's how ei theta b and ei theta c are same here, same with a different sign. Now take these equations and substitute in the final moments. So when you substitute in the final moments, that means what you have found out here, that is MAB. So it is 0.5. Instead of ei theta b, substitute 71.85. So you'll get MAB 35.92. And similarly, MBA, again substitute the values, you'll get this 71.85. Now the check is MBA and MBC should be equal and opposite. The magnitude should be equal, but the signs should be opposite. Okay, similarly MBC, again when you substitute all the values, be careful with the signs also when you're substituting. So it is 71.85, this is minus 71.8. Okay, similarly MCB and CD also should be equal and opposite. So it is 71, here it is a positive answer, here it is a negative answer. Okay, then whatever you've done is right. This is like a check for y'all. And then MDC, okay, so it is a minus 35. Okay, now the most important thing is marking these movements here. Okay, all these movements should be marked in this frame, and after which you have to show it in the bending moment diagram. Okay, now see here, because there is only one loading here, so bending moment takes place, the positive bending moment takes place only in the beam. Okay, so before which we'll just draw this diagram. Now see here, this is a frame. What I've showed here, interiors. Okay, interiors are nothing but the positive bending moments. Okay, I'll tell you how to draw this. Now see here, all the clockwise movements are positive, anti-clockwise movements are negative, right? Okay, now first thing what you've got here is MAB is 35.92, so it's a positive. So positive means at A you need to show it as a clockwise movement. So clockwise means positive like this. So at A it is a clockwise movement. Okay, show it here 35.92. Draw it like this and leave it off. And there is a reason why you need to draw it here. You cannot show it here. Try to draw these movements on the frame itself. Okay, the arrows should touch the frame. The reason why I'll tell you, because later it becomes easy for you to draw in the bending moment diagram. Okay, show it like this. Okay, so next one is MBA. MBA is plus 71. Okay, so again, at B, you need to show a force. So again, plus means positive. Again, positive means clockwise. So show clockwise like this here. So this is 71.85. Now the same moment exists in MBC, but this time it is negative. So what do you have to show it? You have to show in BC span now. Show the moment in BC span. So it is now minus. Minus means anti-clockwise. Show it in anti-clockwise like this. Okay, anti-clockwise. So show both the movements here itself, but write only one bending movement. Otherwise things becomes very clumsy. Okay, so similarly next MCB is positive. So positive I've shown here clockwise, positive. All right, next MCD is anti-clockwise. Okay, so again in this part of this, try to show it out. In this part it is now anti-clockwise. Anti-clockwise means negative. Magnitude is same. And the final one is MDC. So MDC is negative. Negative means show like this, anti-clockwise, negative with the magnitude. Okay, the drawing this diagram is very important. Based on this you can draw the bending moment diagram. All right, so now As usual, we'll start drawing this. Now it is simple. Now you can see here, this is a positive bending moment. It is a positive bending moment. So you can see here, the arrow is trying to push this frame inside. Okay. We have to analyze the frame like this. Okay. So this arrow is trying to push the frame inside. So because it is trying to push it inside, obviously this frame moves inward. This part moves to the right side. So I've shown here from, this is the main original column. So because this moment is trying to push it here, so it goes to the right side like this. Okay, right side. Next, similarly, now what this portion does here is, now you can see here, now we'll take this part of the beam. So if it bends to the right, to keep the beam in equilibrium, okay, at this part, it should bend to the left. Only then right side and left side bending would be considerate. Okay, so now it is bent here. So if it, in this portion, if you try to see here, what it tries to do here is, it tries to bend the beam to the left side. Okay, so this portion tries to bend the beam to the left side. Because it is left side, show it here from the original position, show it here. So it is 71.82. Then join these two. So this part, so this is the column bending moment. Okay, similarly, next in BC portion there is a load here. So free bending moment for span BC is, it's a UDL, so it is WL square by 8. Now it is WL square by 8, substitute all the values here. Then it is 180 kilonewton. First mark this. Then what we have here is, see here, this portion again tries to move upward. All the fixed end moments in the beam tries to move upward. So I'll show here 71.82 and here also 71.82. Then draw the straight line here. Okay, these are negative bending moments, end moments. Okay, then next, again, here if it is confusing to draw this portion, let us start with this portion here. Okay, so see here, this first end D, at D, there is an anti-clockwise movement. It is trying to push this portion to the inward side, inside of the beam. So inside means show this 35.92 like this, inside. Okay, then if it is pushing it inside, obviously in this side it should push it outside to maintain the equilibrium. Okay, so it pushes to the right side. So to right side, how much? 71.82. Okay, so join these two, plus and minus. So all these are minus and this is plus. Show the magnitudes here. 71.82 at all the points. You should show the magnitudes, and at this point also you should show the magnitude at A and D. This is how you draw the bending moment diagram. So this drawing, this marking this moments is very, very important. Be thorough in this, be careful. Okay, if you have any doubts, you can ask me in the session class. Okay, all right, that's all for today. Thank you.